Ever pondered how your messages and transactions remain secure in the digital world where hackers lurk around every corner? Well, the unsung hero of our digital safety is cryptography. Originating from the Greek words kryptos and graphene, meaning hidden and writing respectively, cryptography is the art of secret writing. It's an age-old practice, dating back to ancient Egyptians, and today it's more relevant than ever. In our modern, interconnected world, cryptography serves as the backbone of data security and privacy. It's the invisible shield that protects your personal information, financial transactions, and private communications from prying eyes. Whether it's the secure login to your email account, the private chat with your friend, or that online purchase you just made, cryptography is at work, ensuring your data remains confidential and intact. Imagine a world without this invisible shield. Quite scary, isn't it? Without cryptography, our digital lives would be a playground for cyber criminals. Cryptography is not a one-size-fits-all solution. It has multiple faces. Now let's delve into the two primary types of cryptographic algorithms: symmetric and asymmetric encryption. Symmetric encryption is like a secret handshake. It uses the same key to encrypt and decrypt data. Imagine you're sending a letter sealed in a box, and the recipient has the same key as you to open it. That's symmetric encryption. It's fast and efficient, making it ideal for large amounts of data. But there's a catch. How do you securely share the key with the recipient without it falling into the wrong hands? Enter asymmetric encryption, the solution to the key exchange problem. It uses a pair of keys, a public key to encrypt the data and a private key to decrypt it. Picture it this way. Anyone can lock the box with a public key, but only the person with the unique private key can unlock it. This method is secure but considerably slower due to the complex mathematical operations involved. Each type of encryption has its use cases. Symmetric encryption is often used for bulk data encryption, such as database encryption or file system encryption. It's the workhorse of the cryptographic world, quietly securing large chunks of data with minimal fuss. On the other hand, asymmetric encryption is the star of secure communications. It's used in scenarios where secure key exchange is paramount, such as email encryption, VPN connections, and secure web browsing with HTTPS. But these algorithms aren't without their limitations. Symmetric encryption's main challenge is the secure distribution of the key. For asymmetric encryption, the computational overhead can be a drawback, especially for devices with limited processing power. Despite these challenges, symmetric and asymmetric encryption continue to be vital tools in our cryptographic arsenal. They secure our online shopping, protect our personal communications, and even safeguard the integrity of our elections. These algorithms are the unsung heroes, working behind the scenes to keep your data secure. But how do these cryptographic algorithms know who to trust? Well, the answer lies in the public key infrastructure, or PKI. This system is like a digital notary. It provides a way to create, manage, distribute, use, store, and revoke digital certificates. These certificates digitally link an entity's identity with its public key, and are issued by a trusted party known as a certificate authority. When you receive a digital certificate, you can trust that the public key it contains truly belongs to the entity named in the certificate, because the certificate authority has verified it. Imagine you're sending a top-secret message. You wouldn't just hand it over to anyone, right? You'd want to ensure that the person you're giving it to is trustworthy. That's what PKI does in the digital realm. It ensures that the keys used to encrypt and decrypt data are authentic and can be trusted. Now let's delve into cryptographic protocols, which use these trusted keys to secure data transmission over networks. SSL, or Secure Sockets Layer, and its successor TLS, Transport Layer Security, are protocols used for securing web traffic. They use a combination of symmetric and asymmetric encryption to protect data as it travels between a client and a server. Then, there's SSH, or Secure Shell, a protocol used for securely accessing and managing systems over an unsecured network. It uses public key cryptography for authentication, ensuring that only authorized users can access the system. And finally, we have IPsec, or Internet Protocol Security, a suite of protocols used to secure internet communications. It operates at the network layer, protecting data no matter what application is sending it. These protocols and the PKI together create a secure environment for data transmission. They ensure that your data can travel safely from point A to point B without falling into the wrong hands, And so we see that cryptography isn't just about codes and ciphers, it's about trust, authenticity, and secure communication. It's about keeping our digital world safe and secure, one bit at a time. These protocols and infrastructures form the backbone of secure network communications. Cryptography is not immune to evolution, it's constantly adapting to new technologies. And one of these technologies is quantum computing, a field that promises to revolutionize computation as we know it. But what does this mean for cryptography? Quantum computers leverage the principles of quantum physics to process information in ways that classical computers cannot. This has significant implications for cryptography, particularly for the popular encryption algorithms we use today. You see, many of these algorithms rely on the difficulty of factoring large prime numbers, a task that quantum computers could potentially accomplish much faster than classical ones. So, what's the solution? Enter post-quantum cryptography. This is a branch of cryptography that's developing new algorithms designed to be secure against both quantum and classical computers. It's a bit like building a fortress that can withstand both modern and ancient siege tactics. It's about staying one step ahead, even as the ground shifts beneath us. Now let's switch gears and talk about blockchain, another technology that's intertwined with cryptography. Blockchain is the underlying technology behind cryptocurrencies like Bitcoin. But how does cryptography come into play here? Well, blockchain technology relies heavily on cryptographic principles to ensure security and integrity. Each block in a blockchain contains a cryptographic hash of the previous block, along with time-stamped transaction data. This hash function transforms the data into a fixed size string of characters, which is virtually impossible to reverse engineer. If someone tries to alter the information in a block, the hash will change, making the tampering evident. Moreover, blockchain uses public key cryptography to secure transactions. This allows users to sign their transactions with a private key, which can then be verified by anyone using the corresponding public key. This ensures that only the owner of a particular set of keys can spend their cryptocurrency, providing a robust security measure against fraud. So, you see, from quantum computers to cryptocurrencies, cryptography is always at the forefront of technological innovation. It's a silent guardian, constantly evolving and adapting to protect our information in this ever-changing digital landscape. Cryptography is not just about secure messages and transactions, its influence extends far beyond. Let's dive into the fascinating world where cryptography intersects with cybersecurity and government. In the realm of cybersecurity, cryptography is an unsung hero. It's the invisible shield that protects our data from a multitude of cyber threats. Whether it's safeguarding your credit card information during an online purchase, or securing confidential business data in the cloud, cryptography is hard at work. It's the foundation of trust for online transactions, creating a secure tunnel for data to travel safely. Consider ransomware attacks, a rising menace where cybercriminals encrypt victims' data and demand a ransom for its release. Ironically, it's cryptography that provides the solution. By encrypting data ourselves, we can ensure that even if data is stolen, it remains unreadable. This is why cybersecurity experts stress the importance of encryption as a key defense strategy. Now let's shift our focus to another realm where cryptography holds immense significance: government and military. From the Enigma machine of World War II to the modern secure communications of our defense forces, cryptography has been a cornerstone of national security. It's used to protect sensitive information related to national security and intelligence, ensuring that only authorized individuals can access it. In the military, secure communication is paramount. Imagine a scenario where a military unit needs to transmit their location or plans. If this information falls into the wrong hands, it could have disastrous consequences. Thanks to cryptography, this crucial information can be encrypted, ensuring it remains confidential and secure. Moreover, cryptography also plays a vital role in intelligence. Agencies use it to protect their information while also trying to crack the codes of others. It's a constant game of cat and mouse, where the stakes couldn't be higher. From protecting national secrets to safeguarding your personal data, cryptography plays a pivotal role. This invisible shield continues to evolve, meeting the challenges of an increasingly interconnected and digital world. As we journey further into the realm of cryptography, remember, it's not just about securing messages but about safeguarding our way of life. But is all encryption good, and can it be broken? Well, like any tool, encryption can be used for good or ill. Ethically, it's a champion of privacy, enabling secure communication among billions of people. Yet it can also shield malicious activities, posing challenges for law enforcement. Legally, the landscape is complex and varies globally. Some governments advocate for backdoors in encryption for national security, while others uphold unbreakable encryption as a fundamental right. Now let's talk about cryptanalysis, the art and science of code breaking. From the Enigma machine of World War II to modern supercomputers, cryptanalysts have been trying to crack the code. They use mathematical methods, computational algorithms, even brute force attacks to find vulnerabilities in cryptographic systems. Cryptography is a double-edged sword. It protects our data, but also poses ethical and legal dilemmas, and challenges cryptanalysts to outsmart it.